So we've made this definition of row equivalence, and we've noticed that our definition gives us a genuine equivalence relationship, so reflexive, symmetric, and transitive. And equivalence relationships break up your set of objects into a number of equivalence classes. So row equivalence gives us a collection of equivalence classes where inside of one equivalence class, every matrix in that equivalence class is row equivalent to all the other matrices in that row equivalence class. And these equivalence classes have no overlap, they're mutually exhaustive, and also they cover all of the matrices that exist, and that means they're jointly exhaustive. They cover all the matrices. But in fact, we can do a little better than that, because we know that every matrix has a unique reduced row echelon form, and of course you can get to that reduced row echelon form by doing row operations. So that means the reduced row echelon form for any matrix is in the same equivalence class as that matrix, but of course no two reduced row echelon form matrices are row equivalent to each other, because they represent, if we interpret them as augmented matrices for a linear system, they represent systems that have different collections of solutions. So the upshot of all of this is that each equivalence class will contain a reduced row echelon form matrix, and in fact will contain exactly one reduced row echelon form matrix. And this is a really nice property because for many questions involving matrices, we can actually think about it sort of one equivalence class at a time, and within a single equivalence class we can use the reduced row echelon form matrix in that equivalence class as sort of a landmark or sort of a reference point to help us think about the problem. So let's look at an example. Of course, the tricky part of all of this is knowing what sort of question we can, in what sort of situations does it make sense to use this strategy. And really, we need some sort of question where row operations sort of behave nicely, which really is kind of on a case-by-case basis. But let's look at a couple examples. So suppose that we row reduce a matrix to two different row echelon forms. Do these two row echelon forms have to have the same free variables? Another question we might ask is, do they have to have the same number of pivots? Well, so taking this first one, the same free variables, at first it's really hard to know if they will have the same free variables. It seems sensible that they might have the same number of free variables, but here, I'm being more specific. I'm saying the same free variables exactly. So let's suppose that if we start with some matrix and we do row operations to get to some row echelon forms. So let me call this, I guess, echelon form 1 and echelon form 2. Do these have to have the same free variables? I guess since we're talking about matrices, I guess instead of the term free variables, I should say non-pivot columns. So let me say non-pivot columns. Because of course, a free variable corresponds to a pivot columns if we're talking about systems of equations. Okay, so it's really hard to know how to approach this question, but what we can do is, first of all, observe that these two row echelon forms are in the same equivalence class. They have to be in the same equivalence class because they're both row equivalent to A, right? So we could get from E1 to E2 by doing row operations, by just undoing these row operations and then going from A to E2 with row operations. Okay, so we know these two are in the same row equivalence class, and that means they have the same reduced row echelon forms. So now we can go to the reduced row echelon form. Okay? And the reduced row echelon form of all of these matrices will have certain non-pivot columns. But now think about, how do you get from an echelon form, a row echelon form, to the reduced row echelon form? So what exactly will these row operations look like? Well, these row operations will all be, will take two forms. One is we might multiply a row by a constant. And the other thing that we might need to do to get from a row echelon form to reduced row echelon form is we might have to add a row upwards. We might have to add a multiple of a row to a row above it, right? We never have to go downwards to get from an echelon form to a reduced echelon form. And neither of these operations, multiplying by a constant or adding a row upwards, neither of these change where the pivots are, right? So that means that going from E1 to the reduced row echelon form and going from E2 to the reduced row echelon form, these don't change the pivots. So they don't change the columns that aren't pivot columns either. So that means that, well, the reduced row echelon form, it has certain columns that are pivots and certain columns that aren't pivots. So that means that, well, if these operations aren't changing the pivots, that means all the pivots for E1, for the reduced row echelon form, and E2, all the pivots have to be in the same places, right? These operations don't change the pivots, so the pivots are all in the same place. And that means that, in fact, the non-pivot columns are actually all the same. So must they have the same non-pivot columns? Yes. And must they have the same number of pivots? Well, if none of these operations change where the pivots are, they can't very well change how many pivots there are either. So the answer to this question is also yes. So you can see that even though these questions would have been very difficult to answer sort of at first look, having this knowledge about the uniqueness of reduced row echelon form and the equivalence class of row equivalent matrices gives us a really powerful tool for approaching this kind of question.